Okay, so for today we are going to put them together for modulus. Now, there's two kinds of moduli here, so that's the only reason why I'm keeping it simple like that. Let's go to the first one. The first one is the modulus of elasticity. All right. So this does have another name, and this is also called Young's modulus. All right, it's named after Thomas Young. Maybe you've heard the name before, maybe not. Either way, so it's got both of these names to it, so don't freak out if you see one rather than the other. Now, there's a formula for this. The formula for this is going to be the stress over the strain. Now, in both of these situations, we are talking about the linear stress or the linear strain. All right, so compression or tensile stress and strain. Okay, don't worry, there's another one for the others, but we'll get to that. So there's a formula for that. Stress, remember, looks like that. It's a lowercase sigma. Strain is a epsilon. So there's your formula, but we can break it down further. So a sigma stress is calculated by doing force over area, and then that's going to be divided by the strain. Strain was the change in length divided by the length, the starting length. All right, now that's okay, but no one likes a double fraction. So we're going to juggle it around a little bit. F is up top, A goes to the bottom. Delta L is going to stay there because it's in the denominator, and L is going to jump up here. So this is the formula that you're going to see. You might see this one, and it stands for a letter. The letter is E. E is Young's modulus or the modulus of elasticity, either one. So typically what you'll see is stuff written like this. All right, usually you'll only use two of the three things here. It just depends on the problem, which ones you'll use. So let's do one to practice. So for this first one, we have a steel bar. The steel bar is 10 millimeters in diameter, 2 meters long, stretched with a force, and extends by this much. So we've got all the pieces there. Going to be using our formula. E is equal to stress over strain. All right. I like to write this part out. That way I remember where all the letters go because there's 4 of them. So stress is talking about F over A. Strain is delta L over L, but they're flip-flopped because strain is in the denominator. All right, so then we just got to plug each one of these pieces in. So F is going to be 20,000. All right, times L. L is 2 meters long, but we got to be careful because we want to be in millimeters, so that way it's the same as all the other units there. So let's switch it to 2,000. We're going to divide by the area. It doesn't tell us the area, but it tells us the diameter, so we got to plug it into our formula here. 5 squared times delta L, how much it extends by, so 0.2. So we're going to type all this in, and we are going to get 2.5 times 10 to the 6. All right, so it's a big number. Now, what's the units for this? The units for a modulus of elasticity are going to be the same thing as the stress units, all right? So they're going to be probably in megapascals, just like we were doing the other day. The reason for this is because he has no unit, right? Strain has no unit because you're doing inches divided by inches or meters divided by meters, or in this case, millimeters. So that means whatever unit this guy has here, you're dividing by nothing that will change it. So that means his unit will take over for what the modulus of elasticity's unit will be. So in this case, we had newtons divided by millimeters squared, and that was in our megapascals. So that's going to be our unit. So we got a lot of units here, or a lot of megapascals. If you want, you could bump it up to gigapascals. So this would be let's just go 2,500 gigapascals, right? Or you could go 2.5 terapascals if you want, but usually giga is something they use more often. All right, let's try another one. Okay, so for this one, we've got a steel column that's 3 meters long and this much in diameter. It carries a load of that. Given that the modulus is here, calculate the stress and the strain and determine how much the column is compressed. All right, so first thing, let's just go with the first thing it asks for is the stress. So to figure out stress, we're going to use its formula. We're going to have force divided by area. We know the force is 50 meganewtons. Let's change it to the units we are used to. So we're going to have 50. Mega means million, so we got to add 6 zeros to that number. There's the number of newtons. Dividing by the area, here's the diameter, but be careful here. That's not a millimeters, that's a meter. So if we want to use our normal system, we're going to switch it to millimeters. So we've got this many meganewtons divided by pi, and then r squared. So r is going to be not 400, but 200, right? Because a meter is 1,000, so one back from there. Squared. So once you put all those together, you're going to get 398 megapascals. All right. So there's our unit, there's our stress calculation. Now, if I want to figure out strain, right, I've got a formula for that too, but there's a problem here. Okay? Problem is I don't know how much it's compressed. So what we're going to do is we're going to come at it from the other side. All right? Because I do have a modulus of elasticity here, and I know the stress because I just figured it out. So your modulus of elasticity is equal to your stress over your strain. So since I have two of these things, I'm going to use this to figure out the strain. We'll come back to the green equation in a little bit. So I've got 200 for my modulus of elasticity. Now this is in gigapascals. It's got to match whatever my stress is in. So my stress is in megapascals, so I'm going to move this down a unit. So this is going to change to 200,000 because that's megapascals right there. And that's going to equal the stress. The stress is 398 divided by your strain, which means that your strain is going to be what you get once you divide some of those numbers together, which is 0.001989, 0.002 basically. All right, no units for this because remember strain is unitless, length divided by length. So once we have there, now we can figure out how much it's compressed. Okay, we know the strain. The strain is 0.001989, and that is going to equal our delta L divided by our original length. Our original length was 3 meters. So we can just leave it as there, and our answer will be in meters, or we can switch it to millimeters if you want. I'm just going to leave it like that for now, and we'll see where we end up. So this, after we do our calculations, our delta L is going to equal about 0.006. Now, since our L was in meters, our delta L will also count in meters. So let's switch this to something more reasonable. Let's switch it to millimeters. And there we go. So we're going to be using all three of these formulas together sometimes. All right. And in case you're surprised, well, there is another version of this. It is the modulus of rigidity. So this is only different in that this is using shear forces. So this is shear stress and strain. Okay, so the other one is using tensile or compression. This one is using shear stress and strain. All right, so modulus of rigidity. Yeah, that's what it's called. There's some other names for it too, but either way, the letter that they use for this is G. So for this formula, we're going to have G is equal to tau divided by gamma, right? This is your stress from before. This is your strain from before. These are just your shear stress and strains. Now, if you really mix up the letters, is it going to matter? No. As long as you know what you're doing, the letters aren't as important. So this is going to equal, just like before, your stress is going to be your force over your area. Your strain is going to be your delta L over your L. Now, when you put them together, they're going to flip-flop the denominator again. So F over A, L goes on top, delta L goes on bottom. And it's basically the same exact formula we saw a little while ago. It's going to work the same way. It's just measuring shear forces instead of linear forces. Let's do a practice. So for this one, we have a steel rod under a shear stress of that and a strain of this amount here. What is the shear modulus of steel? Well, the shear modulus of steel is equal to your stress over your strain, which means that we just have to divide those two. Okay, so we have 240 megapascals divided by 0.003. So we divide those two numbers together, we are going to get 80,000. What are going to be the units? The units are going to be the only units you have written down here, which is going to be megapascals. Now we can bump this up to gigapascals. Does it really matter? No, as long as you're doing something reasonable. That's what they're going for here. Okay, that's all we do for that one. Let's do one more. We got one more, it looks like. Concrete beam is under 50 KSI of shear stress. What's the final length? The initial length is 6 inches. Modulus of rigidity of concrete is this number here. Okay, we wanted to do one of them in a different unit just so that we can get acquainted with it, just so we can at least see how it's the same thing. All right, KSI is something you might not have seen before. KSI is simply 1,000 PSI. All right, since it's 50 KSI, that means the stress is going to be 50,000 PSI. All right, but let's kind of set this guy up here before we get ahead of ourselves. So G is going to equal your stress over strain. Now, we don't have to break apart stress because we know what stress is as a whole here. So what we're going to do is we're going to break apart the strain, but not the stress. So this is going to equal our stress times L over delta L. All right, so we broke apart the strain separated into its two pieces, but the stress we're just leaving together because we don't need to break it apart. We know what the answer is. So now we're going to plug in the things we know. The modulus of rigidity is 3 times 10 to the 6. Now this is in PSI, so we got to make sure everything else is in PSI here. So our stress was in KSI, that's why we got to switch it to PSI. So we're going to have 50,000 times our L. L is 6, right? 6 inches divided by our delta L. All right. So now we just got to solve this all out. Our delta L is going to equal 0.1. All right, what's the units for this? The units for this is going to be the same as the units for here, right? Because these guys will always be the same unit, so they cancel out. So since he was in inches, this one is going to be in inches. Now we're not quite done yet. We're almost there. It didn't care about the delta L, it wanted the final length. So what we've got here is if we started out at 6 inches, and our delta L is going to be 0.1, what's the new length going to be? Well, the new length is going to be 6.1 inches. All right, because it's a shear stress, so that means it's, twisting, it's growing, right? Because remember, shear stress means that it's sliding out like that. So what we know is this length here is going to be bigger than that length there because of the shear forces that are at play here. Okay, that's the last one. Hope you had fun. Like and subscribe.